So, GPU programming in Julia. I'm going to give a introduction of about 45 minutes an hour on how to use the several GPU backends that we have in Julia with a focus on CUDA.jl, but most of the concepts here are going to be portable across the other backends I'm working on, which is Metal.jl for Apple GPUs and OneAPI.jl for Intel GPUs, and there's also AMD GPU.jl maintained by other people for AMD GPUs. But before all that, I'll maybe very briefly mention, that's right, what a GPU is. So most of you will be probably familiar with GPUs as being massively parallel hardware accelerators. As you can see in this very small diagram, typically a GPU consists of multiple processors called streaming multiprocessor with some global memory. Every streaming multiple processor has its own memory as well. And crucially, you as a programmer, as a kernel writer, will have to manage how you use these memories much more manually than you're typically used to doing so with a CPU. There's a bit of shared control logic, but the focus with these streaming multiple processors is much more on a very large register file and lots of ALUs to perform computations. This has some consequences. So comparing to a CPU typically has few but powerful independent general purpose cores, whereas GPUs have many more, but much more lightweight and often cooperative threads. Comparing all of that together, you typically have a very high bandwidth bus to feed all of these threads with sufficient data. So what does it boil down to? If you want to program a GPU, you typically require different effective algorithms that know how to address this huge amount of parallelism in a way that also efficiently uses the resources you have at your disposal. For example, you cannot be going to global memory all the time. You actually have to optimize the implementations you're using that shares the memory that's available on your streaming multiprocessor. Threads execute cooperatively, so you have to be mindful about code executing in lockstep and so on. The second, so this is up to the programmer, up to you as the kernel writer, or up to the library implementer, us creating these codes for you. But because these threads are very lightweight threads, there's another dependency, and this is more on programming language, namely that the code that you write has to get compiled to something that's high quality, statically typed, predictable, such that the GPU can execute it efficiently. It cannot be general purpose code that, for example, there's plenty of allocations or there's plenty of data dependent branches. The code that has to be generated has to be fairly high quality code. And this is, of course, where Julia, the language, comes in. So for a bit of history, Julia is a high-level language, of course, as you've all seen today, which has always been designed with performance in mind. At high level, you can do very simple stuff. For example, here you have the genius tuple of an integer, floating point number, and I'm computing the sum. This is very high-level code you might want to write interactively in your REPL. However, because Julia has been designed with performance in mind, really, we get this very high quality, in this case LLVM code, out of that representing this sum operation. So you can easily have a look at the compiler generates where you that code LLVM macro in front of your CPU button. And we can see here that this is well-typed, predictable, straight line machine codes that subsequently can be compiled down to very high quality efficient CPU codes from AF64 and such. And I want to emphasize that this is not a given. This is because the language has always been designed with performance and compilation in mind. Many more details in this paper that has been written by Jeff, but a handful of crucial details here. Julia uses machine native types, so we don't see the fault we begin to build or arbitrary certain point numbers. We use things that the machine can represent. Even though your program is entirely dynamically typed, so there's no types in here, the compiler will actually analyze the code and propagate type information throughout the program, such that it can use that type information to then, for example, de-virtualize function call, meaning a function call is not, for example, the sum function. The compiler knows exactly which sum function we are calling, allowing it to generate specific code for this sum implementation. Anyway, these are details. However, the fact that Julia has been designed with this kind of compiler model in mind allows us to just retarget the compiler and target PTX code, which is the instruction set architecture that we need to target for NVIDIA hardware. So this sum function can just start being compiled for GPUs. And the result of that is, of course, that we have developed and we have plenty of GPU backends in the Julia language that are all built on this compiled language generating high quality GPU machine code. It has some advantages over the typical vendor tools, namely that you're working with a high-level language. So generally, we expect you to be more productive than as you work writing GPU applications in C or C++. However, importantly, because Julia is a compiled language, you can still write your low-level kernel. You can still get compiled down to machine code. So within the same language, you can go from the high-level explorative GPU programming and move all the way down to the kernels that then developer might have to develop because of performance reasons or flexibility reasons. So there's a couple of backends, CUDA.gel for NVIDIA hardware, as I mentioned, AMD CUDA.gel for AMD hardware, OneAPI.gl for Intel hardware, and Metal.gl for Apple hardware. There's a couple of other backends that we use, the stack that we have developed, which is called the GPU compiler stack, with our strictly speaking GPU, so kind of ignore them for the remainder of my talk. So even though we have plenty of backends, most of them follow a similar design or a similar paradigm. We aim to be very user-friendly, so it should be possible to get started with GPU programming in Julia really quickly. It's all the package, and you should be all set. At the same time, we don't want to take the flexibility out of your hands because people are inevitably either wanting to implement advanced stuff or people who are familiar with the low-level stuff may end up having to work with Julia. So we want them to be able to do what they're good at. We also offer multiple programming interfaces. And lastly, we also want to offer the ability to write code that executes across different GPU vendors. So I'll be going into detail on each of those. The first step being that everything should be user-friendly and easy to get started with. And one way of doing so is that we try to minimize the dependencies that you as a user have to set up. Typically, if you want to use NVIDIA GPUs, you have to install NVIDIA drivers, you have to install the toolkit, you might have to install some libraries, and you have to make sure everything is consistent and discoverable by whatever tool you're using. In Julia, we have this thing called an artifacts system, where we can actually ship binaries to you that we have repackaged and decided which one you have to use based on your system. And in the case of CUDA.gl, the only thing you as a user still have to install is the NVIDIA driver. And after that, really, the only thing you have to do is enter the package manager, you add CUDA, you're using CUDA, and when you perform the first API call, for example, here the version info call, which is a good way to quickly have a look of what configuration your system has to offer. So automatically downloads relevant artifacts. In this case, it's HB toolkits, maybe quickly and then maybe 2 class, automatically download that, set that up, and we will mention which libraries will have to be downloaded and which devices will have to be discovered. And the same applies to other backends. So maybe for those who want to follow along, this may be a good time to try and use your installation of Julia and install any of these packages and maybe try and follow along with some of the things we'll be explaining. Because it really is that simple. So for example, in the case of OneAPI, if you have a laptop with an Intel GPU in it, and you're running either Linux or you have WSL, for Linux, you can similarly just add OneAPI using OneAPI, and you even don't need to install a driver because with OneAPI we can ship the driver to you. With metal, you need even less, you just need a sufficiently up-to-date version of macOS. At this point, we require macOS 13 or higher, which most Apple users should already have installed. And similarly, you just install the Metal library and you're good to go. AMD GPU.jl, I don't have experience with, but it is a similar procedure. And lastly, if you sadly do not have a GPU, you might still be able to use our experimental OpenCL wrapper, which does support CPU execution. And this is never going to become or at least we don't anticipate it becoming one of the important backends that we have in the Julia GPU ecosystem, but it can be relevant for certain embedded devices, and as demonstrated here, it can be relevant for CPU execution when you don't have a GPU at your disposal, but you still want to execute some GPU codes that probably has developed, for example. If you want to try OpenCL, be sure to add #mask, which will install this version of OpenCL.jl, which we're actively working on. I also mentioned flexibility. And in order to do so, we perform certain simplification of the typical programming model. For example, if you want to use Metal in Objective-C, the first step almost always will be to look up or create a device to execute code on. Then you have to create a command queue. Similar things are required in one API or OpenCL. Whereas with Metal.jl, we provide you with the default implicit device object and default implicit command queue object, resulting in you just being able to ask methods of a function. This will automatically execute on current device with the default command. However, crucially, we do not want to take this control out of your hand, so it's always still possible to call these functions to instantiate your own device, instantiate your own command queue, and use that for your application. So again, trying to balance user-friendliness with flexibility. But by default, the idea is that you can get started with these frameworks really quickly and really easily. I also mentioned that we have multiple programming interfaces, multiple levels which you can use the GPU. The highest level is obviously the application level, which I'm not going to delve too deeply in it, but as an example, the Flux package, which is one of the machine learning packages in Julia, has this magical GPU function. And you can just throw things at this GPU function, throw data at your GPU function, and if you call your model with data, it will execute on the GPU. This depends heavily on the application. You have to consult the application documentation and in what way GPU are supported. But it's not that relevant or interesting from a GPU programmer perspective, because ultimately it's up to the application how to expose the functionality that we've developed. The array programming level is one of the easiest ways to get started with GPU programming, because arrays in and by themselves, they typically expose lots of parallelism because of, well, having many items, elements in your array, and you're typically either doing element-wise operations or other operations on arrays that by default expose some level of parallelism that we as array library implementers can expose or benefit from in order to operate these, to execute these operations on GPU. Every GPU package has its own GPU array type, but they behave very similarly. For example, CUDA package, CUDA.jl has its full array type. So after you've imported the CUDA package, you can use the full array type. For example, then I'm using it, calling its constructor, feeding it some data that's been allocated on the CPU. And if I then perform operations, for example, here I'm logged as a sign function, which is an element-wise operation of every element of my array. Then I'm computing the sum of this array. Both these operations will execute on the GPU by virtue of us having implemented these in CUDA.jl. And this is in part because of how Julia has been designed. It's because of Julia's array abstraction, but it's also because of Julia's multiple dispatch mechanism, allowing us to redefine functions like sum or broadcasting sign, which are defined in base, and we redefine them in LGL, which GPU optimized implementation. And it also benefits from the fact that many code in Julia base is fully untyped, meaning that it can equally well operate on CPU arrays as it would on GPU arrays. If base was locked down on the CPU array type, and it would be possible for us to feed GPU arrays into it and reuse all of the code. So the beauty of generic code and multiple dispatch makes it possible to reuse lots of code and execute it on GPU. And the goal with the array types that we designed is to make them as compatible as possible with the official array type in Julia base. So you can start out optimizing or implementing your application on the CPU using the array type, and then ideally port it to the GPU by just simply switching the array types from your application. So operation side, for example, creating a view, forming a sum, doing scalar multiplications, taking the adjoint, doing matrix multiplications. All of these typical operations you might be familiar with because you've done them with CPU arrays should equally well work with GPU arrays, but then execute on the GPU instead. Where possible, we also try to integrate with standard libraries or external packages, especially on the CUDA front, because NVIDIA has a rich ecosystem of vendor libraries. There's, for example, Courant, which provides lots of random number generated functionality for the GPU, which we tied in with the random.jl standard library. So if you call the length bank function, which is a function to fill an array with random numbers, if you call that function with GPU array, we will automatically dispatch to the Courant library from NVIDIA to give you the highest quality and the fastest implementation of that operation. cuBLAS is another library by NVIDIA, which all kinds of linear algebra functionality, which obviously is linked to the linear algebra, the GL, standard library, cuSparks is integrated with Sparks arrays, cuFFT is integrated with abstract FFTs, and so on and so forth. And similarly, the same applies to other packages. AMD GPU .gl also has this kind of integration, OneAPI and Metal to a lesser extent, mostly because, for example, Metal, Apple doesn't really have this exhaustive of a set of vendor libraries to integrate with. And in that case, we have to implement our own versions of these operations. And that's, of course, quite a bit work, which we haven't always done for all of our backends. But the real beauty of array abstraction comes in with higher order functionality, because up until this point, an array type that dispatches to Courant, I mean, this could as well have been implemented in Python or in any other language. One of the unique things we can do in Julia is enabled because we have a JIT compiler. For example, here I call the map function on Courant, but I'm also feeding us some custom user-defined code that indicates that every element has to be incremented by one. And this is actually a combination of a library function, the map function, which we have implemented, and a user function, x+1 for every element. And this is only possible because we have a JIT compiler, so at runtime, we can actually compose the two implementations together, the map function that we have library programmers have implemented, and the user function that you have provided. This can be written a lot more compactly, succinctly by doing these dot operations. So behind the scenes, if you do A dot plus to B, it's actually going to compile a new function that compiles the implementation of our broadcast abstraction with this operation that you specified and generates a new kernel. And we have plenty of these higher order abstractions. The reduce function, for example, the first argument to reduce function is the operator has to reduce over. We have a similar function to accumulate, define further function, and feed it with predicates. So these kinds of abstractions are only made possible because we have a compiler, because we can compile code at runtime, which is much harder when you have a fully pre-compiled library like one written in C or C++, which does not have the ability at runtime or at compile time, even when you feed it to the function to generate in the kernel. And this kind of programming pattern is really powerful. This is always an example I show taken from this course, which is the Julia forums. a couple of years ago, where a user has implemented a very, very simple machine learning model, which was proximal gradient descent training loop, some manually specifies loss and gradient functions. By default, it executes on the CPU because the inputs, the weight, and the bias are all allocated as arrays on the CPU. And the way you, quote unquote, port that to the GPU is simply by switching the input output and the weights to the current output. And as a result, all of these operations, for example, the sum operation, the broadcast, the multiplication, all of these operations are automatically going to be dispatched into GPU optimized applications. And as a result, you get some performance benefits. It's mediocre one at best. It's not optimized. It's a perfect example. Nonetheless, it demonstrates the idea of array programming being sufficiently powerful to allow you to quickly move code from the CPU to the GPU or to any other accelerator. But as I mentioned, it is cherry-picked in that every example, every abstraction call in here is GPU compatible, either because we have implemented it or because it's just fundamentally so. Some abstractions cannot be efficiently executed on the GPU. So for some of these, for some of your applications, you might still have to implement your own custom kernels because we don't have an abstraction that fits your bill. And this is the other advantage of having a language in which you can define your own kernels. So within Julia, it is both possible to use these fully automatic array abstractions, but if they don't work for your application, it's always still possible to write your own kernels within the same language. This is comparing how you would do it in CUDA C, where you have a bunch of host operation. It's CPU, it allocates CPU memory. This is your kernel function. With this triple angle bracket implementation, you launch this vector addition function over 512 threads on this data that you've allocated. And this is the equivalent in Julia using CUDA.jl. The host code is, in my opinion, greatly simplified. You have to use fairly level malloc in this simply called two-way constructors. The device code, however, is similar. And this is on purpose. So typically at the point that you start writing your own kernels, you know what you're doing. And there's a reason you're doing so. Typically because you want to squeeze all of the performance or you need flexibility that kernel programming has offered. And because of that, we stuck to the same level of abstraction for programming kernels in Julia as if you have in C++, making this a relatively familiar environment for people who already are confident or familiar with writing kernels in CUDA-C. Sometimes we do a little changes for the sake of consistency. For example, in Metal, your thread position is normally an argument to a function. We've changed that in Julia to be a function call, so that it's again similar to how our other GPU backends work. With one API, we've taken some more liberty of moving away from this parallel line TSL into this relatively familiar and similar scalar programming model that we have for CUDA and Metal and all of the other backends. And this enables kernel abstractions to target all of these backends equally, which I'll get to later. And even though all of these backends have seemingly lots of differences, the programming model is familiar, and we've also made sure that there's a strict set of core functionality that's available in all of our backends. So you have the obvious indexing intrinsics, which is something you need when you write kernel code. Every thread that executes needs a way to query which elements the thread is currently working on. These are the indexing intrinsics. We support shared memory in all of our backends. Shared memory is the memory that's allocated on the streaming multiprocessor that you're executing, which you have to use for performance reasons. You're usually going to global memory all the time. We also support, to some extent, temporal operation and atomic memory. And with this set of functionality, you can implement 95% of all of the kernels that you would ever need. If you need more advanced features beyond that, CUDA.gl is the way to go. Some more advanced features like dynamic parallelism, calling kernels from kernels, doing cooperative kernels, or addressing defensive calls, for example, to implement your own matrix multiplication functionality. Things like that you'll only find in CUDA.gl, which is by far the most mature backend, but nonetheless, with this subset, most of the time, this will cover all of your needs. And if you want to see what's happening behind the scene, I mentioned this add code LLVM macro in the beginning to have a look at the CPU code. So we have device underscore equivalents for all of our GPU backend. For example, with CUDA.gl, you can do add device code PTX of whatever code that calls a kernel. In this case, it's a direct kernel call. But then you can see the PTX code that's been generated for this function. This is again a vector addition function that I demonstrated a couple of slides earlier. So you can again see that this is very straightforward, straight line, high quality machine code. This is the same with Apple hardware, where you use device code AGX. This is the SPIR-V backend, which we use for OneAPI and OpenSCL for gel. So again, we strive to, even though it's multiple backends, you have similar tools that are similar across all of our backends. Having a look at the generated code can be useful. Sometimes people do this for performance optimization purposes, but the first step is always to actually go in and benchmark your code and profile your code. And for that, we offer tools and utilities as well. And you might think, well, I can just use add time or benchmark tools. I'm showing the slide because there's one thing you have to be mindful for, is that GPU operations are by default asynchronous. So if you call this operation E dot plus reverse of A, this will not wait until your computation has finished. This will enqueue the operation. And only when you fetch the results by calling the array constructor, for example, or by calling the copy-to function, only at that point we will wait for the GPU to finish computing. And this, of course, is bad if you want to benchmark code. But if you want to benchmark GPU code, always have to wrap your code with this CUDA.add sync block, which is going to synchronize. We have a shorthand for this, which is CUDA.add time. Gives you some additional insights in the amount of memory allocation. So this is predictable. The reverse as the third one memory, then the broadcast as the other, and then basically allocations. This is composed with benchmark tools. So if we do benchmark tools, always CUDA.add sync. Unless you know that your operation itself is synchronizing, but most of the time it isn't, and then you have to use CUDA.add. In the case of CUDA.gl, we also have a native profile. So you can do CUDA.add profile, your operation, and then you'll see two tables. One table explains you what has happened on the CPU. The other explains what has happened on the GPU. And this is relevant because you can use it to have a quick peek at how efficient the use of the GPU was. In this case, 90% of the trades, the GPU was actually busy, which is pretty good. But in some cases, you might have a very low utilization. You can see while actually doing huge amounts of kernel launches, for example. And this you can see in the CPU table, illustrating that you're probably launching too many kernels. So, most vendors also have graphical tools. For example, CUDA.gl has Insight Systems, which you can run CUDA Julia under your GPU application, and you'll get a nice visual representation of what I've shown before. So this is we call it the reverse kernel, called the broadcast kernel, and you can nicely see that the GPU was busy quite some time executing these kernels. Metal.gl has Xcode and instruments to run the application on the AMD GPU.jl has Rockcroft, and one API has DG. So these are all very similar applications that are available across the Julia GPU ecosystem. Well, actually across the GPU ecosystem, but we made our packages so that they are compatible with all of these tools, you know, they work nicely together. This is a more realistic application where I'm actually doing many more kernels. I'm showing it to illustrate that with CUDA.jl, you can also use the NVTX library to add additional CPU information into your GPU timeline. And this can be very useful to, for example, if you're not sure which function is slow or which function should be optimized, if you add a couple of these ranges to your CPU application, then you can nicely see how much time was spent. So all of these gray blocks are NVTX ranges that I've added to my application. You see the cascade I started to update my main function, started by finding the calls that were slow, and this is a visual way of drilling down to the GPU application that is the GPU operation that is slow and has to be optimized. And with NSI compute, you can even dive into individual kernels, which tells you the percentage of speed of flight, which is a theoretical maximum usage of the GPU in terms of compute and memory bandwidth. And you can use that to really micro-optimize individual kernels should you need to. And the result of all that is that this integration has also allowed us to really optimize our own kernels that we have implemented. A couple of years ago, we did an analysis of the CUDA.jl compiler by hooking the NVIDIA parallel programming benchmark suite. And the result was that on average, we were even a little faster than C. And this wasn't because of how Julia was designed, but this was also in part because of the fact that we were using LLVM and NVIDIA was using their own proprietary backend at that time. Nonetheless, it does show that we don't have any overheads overwriting your kernel into that scene. This is a much more recent work where we implement our own matrix multiplication kernels in Julia, comparing to Kubernetes and Cutlass, which are both state-of-the-art pieces of NVIDIA technology implementing matrix multiplication. And once again, we're really performing well. Of course, this still required somebody knowing how to implement matrix multiplication kernel efficiently on the GPU produced in Julia, but nonetheless, using Julia in and by itself doesn't cause any overhead and it allows you to do really high performance GPU computing. This is similar work with AMD GPU.jl where performance compared to HIP C++ was again virtually negligible. So the same thing applies here. The other backends have not been as greatly optimized. So one API.jl and Metal.jl they aren't at the top of their performance game, which isn't bad because those two backends are typically available in laptops anyway. So it's a good way to port your application. For example, if you have some high performance application and you have an Apple GPU, it's typically useful to be able to port it locally on your laptop, make sure that everything's GPU compatible, and then porting it to the actual supercomputer with NVIDIA GPUs will be much easier. Same thing applies for Intel GPUs and many Windows laptops. So we're mainly maintaining those to make it easier for developers to develop these codes and make sure it's all GPU compatible. All right, so the next big thing to discuss is portability. Because up until now, I've been discussing the backends in isolation, showing everything you can do with all of the backends by themselves. If your code is written with just array operations, it's already pretty portable. Typically, the only thing you have to change is the array type. And I'd say it's mostly portable because it's always possible that some operation that's supported well by CUDA.jl doesn't work as well with GPU.jl, for example. So there might still be some experimentation and some specialization to be done. But in general, the code that you've written is fairly portable if you're using array operations. For kernels, that's not true, and that's why the package called kernel abstractions exists. It is a package that provides a kernel programming abstraction, making it possible to write an as kernel function doing exactly the same things, but with generic names that can then be compiled or mapped down to whatever backend specific operation is available in the backend you have to use. For example, for indexing, where in CUDA we have thread IDX, where in YAPI you have group size and so on. We use the at index, we add group size matrix. Check memories at local memory, as private memories, the memory that's only visible to the kernel itself. Yeah, just call thread synchronize in CUDA, now call at synchronize in kernel instructions. So again, all of this showing that there is a very straightforward mapping between these kernel abstractions and what the backend is exposed, making it possible to write kernels that can almost trivially get compiled down to whatever backend you're using. And this makes it possible for kernel abstractions to equally well perform very good. Much of the diffie stack, which empowers the whole SciML ecosystem, has been ported to the GPU using kernel abstractions and performs really great across the board. There's people working on fluid simulators, on ocean simulators, all of that built on top of kernel abstractions and performing really well, essentially. So the performance that we have with the individual backends really carries over to code that has been written with kernel abstractions. All right, so far the overview. I'm going to show how all this applies to a very trivial operation. The operation I've chosen is the computing the root square error of a matrix. It is a very trivial operation, of course, but it demonstrates a few core concepts. So you have some scale operation, you have a reduction to a sum, and ultimately you return scalar, so it's an item of the whole. The way you would trivially implement this on the CPU is really using this fairly legible expression. You execute it by allocating some data. We're going to be working with 2048 by 2048 single precision for the point numbers, and I'm using the benchmark tools package to do benchmark this function, executing in about 3.5 microseconds. Porting to the GPU is trivial because we can just retain the definition. Instead of raise, we use coolRaise. We crucially disable scaled iteration. This is something I haven't mentioned yet, but in the cases that you're calling an array operation that has not been optimized or implemented for the GPU, we will typically fall back to a generic implementation in the Julia base standard library, which oftentimes uses for loops to compute something element by element. And the way that happens is literally element by element. So every element is going to get copied from GPU to the CPU. It's going to perform the operation on the CPU and it's going to upload it back to the GPU. And this is extremely slow. We call this scalar iteration, and you can disable this by following this flag. This will make sure that you cannot accidentally fall back to extremely slow functionality. So here, because I'm supposedly really important something for performance, I'm disabling it. And out of the gate, you already have very significant speed improvements, going from 3.5 milliseconds to 57 microseconds. And the question, of course, can we do better? So the first step is let's profile this application. And here we can see that the actually goes 2.6% of the space. Do note that the total execution time has been multiplied by 3. And this is illustrating that there is a certain overhead associated by running under profile. That's inevitable. Nonetheless, ratios typically should be similar. So here we actually, the activity of the device is fairly low. And one of the reasons here, if we just problem on the kernels that we're launching, you can see that we're launching 4 kernels, and all of these launches are taking around 20 microseconds. And this is also very important to remember. If you're using a GPU for very small operations, say, some 100 by 100 matrix inputs, that's not going to be worth it most of the time, because just the time to launching the kernel is often going to dwarf the time that it would take to perform this computation on the CPU. In some cases, it may be worth it, for example, to keep data on the GPU, not having to copy it back to the CPU to perform the operation on the CPU and then upload it again, to keep everything on the GPU. Sometimes it's interesting to perform slow operations, but in general, you want to avoid having to launch too many kernels because launching kernels is not free. And here there is actually an easy way to avoid these additional kernel launches. And this brings me to the general advice of how you optimize array applications in Julia. Typically by pre-allocating your outputs, by preferring in-place operations instead of out-of-place operations so that you don't have allocations within your loop, and also by fusing operations together. And it's the fusion here that's very relevant for our Julia application. Because simply by adding this additional result here, these two operations now become one. So when we first did A minus B subtraction, and then the broadcast square by 2, if we add another dot, these three operations are going to get fused together by Julia compiler into a single operation. As a result, a single kernel launch. And you can see there's lots of benefits to implementation on the CPU. CPU time also well. CPU time improves a little bit, but nonetheless, it's an improvement. You can even go one step beyond that. If you're familiar with how base of broadcasts work, which yarns, it's just to illustrate that it's possible to peek behind the layers that the abstractions offer you. It's actually possible to use the whole scalar operation within the sum computation, resulting in a single humongous kernel doing both the reduction and the scalar operation. On the CPU this time, instead, the regressive performance, something to be looked into at the time, but on the GPU, further improves performance again by avoiding kernel launch. And what's important here is that ultimately, this has been optimized to some steps. Nothing about it is GPU specific. This is still a fully generic, fully untyped operation that can be applied to any kinds of array abstraction. And this kind of generic pattern makes it possible to write highly generic codes that composes lots of functionality. It's one of these underappreciated, at least the people use the language, components of Julia, that because of code is written for generically, it's really possible to take pieces of code from all across the ecosystem and try and piece it together. It won't always work perfectly. The libraries themselves have to be designed in a certain way to allow this composition. But if it does, then it works beautifully. For example, here, user has written some function f. I'm mapping this function f over a distributed version of a GPU array with dual numbers. And this is composing functionality from all of us. So this is the user function. The map function is generically implemented in GPU arrays using kernel abstractions. The distributed function comes from distributed arrays, dual numbers and forwarded, and dual array comes from together. As a result, all of these packages are fairly small. I mean, the total amount of code that's involved in this is fairly limited. Nonetheless, it allows you to implement these really powerful abstractions, especially for initial prototyping, for initial explorative programming. If you profile this, you might notice that one of these doesn't compose perfectly well together, or there's some performance being left on the table. But well, then that's how it is. You're still in the same language. You still have the ability to go in and optimize further. So let's profile the final version that we have implemented. Performance is a lot better. Well, still with the overhead of profiling taken into account. And we can see that we went from 4 kernel launches to 2 kernel launches. And this remaining kernel launches is because of how our mapping is currently implemented in CUDA.gel, performing a 2-step reduction depending on how large your data is. And this may be a good opportunity to, for example, go in and define your own kernel, which is what I'm going to do. Mostly as an illustration that implementing GPU code is not really easy because you have to know how the GPU works. So if you implement your own kernel, you'll typically have to write two pieces of code. One is the code that actually executes on GPU, on kernel function. Then you have your post abstraction. In this case, it will be RMFC function taking two array inputs. And for example, it has to do some checks. It has to allocate an output container, it has to initialize the output container. It has to determine the launch configuration, how to invoke GPU. And then finally, it calls the kernel function with that launch configuration. So this is the generic stuff. If you look at the kernel naively, so we have to use completely together. You might have every element to atomic addition of the scale parts, and then return that in one element. It's maybe a naive implementation of your initial function, kernel function, and it would forward. Because the one mistake that it makes is that it goes to global memory all the time. As I mentioned earlier in the beginning, GPUs have global memory that's shared across all threads. They have the local memory that's shared with the multiprocessor. So here, really global memory, and storing global memory. As a result, we're not benefiting from, we're not doing what GPU is supposed to do. And we write to kernel instead. So the first step to optimizing this is to accumulate in private value. Every thread has a private value. It has a while loop for partial reduction of a couple of elements. We now only write this once at the end of the global memory. So we're reducing global memory a little bit already. And well, this is a very big improvement. Nonetheless, it's still slower than the original array implementation. We're outperforming the CPU already, but that's not difficult. If you really want to optimize this, you probably have to do some tree-style kind of reduction, where instead of reducing the final value immediately to global memory, you can first send it to another thread. Another thread is going to be aggregating a couple of values, and so on and so forth, until you only have to do the atomic scope of global memory once per shared multiprocessor. And this is the point where we finally outperform the initial array implementation by unlocking 10 microseconds. So this is to show that implementing kernels isn't trivial. It's generally something you drop down to. It can be it's fun to do. I recommend you to take a look at how kernels are implemented, but nonetheless, it's not trivial. It's something you do when you have to squeeze performance of some operations. So can we do this portably? Well, sure. Not entirely. Because the grid style reduction I showed, where every thread is accumulating a couple of values, it's not easy currently to implement this in kernel abstractions. So in our kernel abstractions version, I'm still doing one element per thread, and then we see that. And again, this tree style action. As a result, performance regresses a little bit. Nonetheless, this is a fully generic implementation that's executable on all of our GPU backends, which is great. I also want to mention that we are in the process of moving towards kernel abstractions more and more. We're rebuilding, for example, the GPU arrays package on top of kernel abstractions. So I expect further improvements on kernel abstractions down the line. Yeah, hopefully this in the future version of my slide deck will maybe even outperform the version shown in my previous slide. And this is where I'm going to keep it for the first part of my presentation. So as an overview, Julia is a great language for CPU programming because of this being designed for performance, and this allows us to do on the GPU. And as a result, we have many backends and all follow the same paradigm where you have the very user-friendly array abstraction. And once you have to optimize, you can benchmark, you can profile, and with the same language, you can implement your own kernels. And if you use kernel abstractions, it's all perfectly well. We have websites, GPU.org. We have some learning resources on there, some links to documentation. We have a blog. So every time there's a big release of any of the packages, there will be a short entry on there explaining what has changed. So if you're interested, check that out. I propose maybe I'll